The robotics community has been buzzing about a new announcement claiming to open source a humanoid robot called Asimov V1. The headline promises a breakthrough in democratizing physical intelligence, specifically targeting a price point of $20,000. On the surface, this sounds like the culmination of years of effort to make advanced robotics accessible to individual researchers and hobbyists. However, the reality of this announcement is far more nuanced than the initial headlines suggest. To understand what is actually happening in the field, we need to peel back the layers of the announcement and look at the distinction between the hardware and the software. The research indicates that the Asimov V1 announcement refers exclusively to a software initiative focused on semantic safety rather than a physical robot. It introduces a framework for generating robot constitutions to align AI behavior with human preferences. This is a massive achievement in the realm of artificial intelligence and safety alignment, achieving an 84.3% alignment rate in benchmarks. But for those waiting for a physical machine to walk off the shelf, there is a critical knowledge gap. The confusion arises from a corrupted source file that suggests a physical robot exists, alongside other unrelated releases like humanoid world models. Consequently, the field currently distinguishes between accessible hardware and advanced safety alignment tools, with no evidence supporting the existence of a physical Asimov V1 robot. This distinction is vital because it changes how we evaluate the state of open-source robotics. While the software layer is being standardized through the Asimov framework, the physical hardware landscape is being built by different initiatives. The Berkeley Humanoid Lite and the AGILOped are the actual open-source platforms designed to lower entry barriers for physical research. These are the machines that are being 3D printed and customized. When we talk about the engineering trade-offs required to achieve a $20,000 price point, we are talking about these physical platforms, not the Asimov software suite. Understanding the hardware decisions behind these machines is crucial for anyone trying to build or buy an open-source humanoid. Let us look at the actuators, which are the muscles of the robot. In a proprietary system, you might find high-end electric actuators with integrated harmonic drives and high torque density. These components are expensive and difficult to manufacture at scale. For the open-source community aiming for that $20,000 target, the engineering challenge is finding a balance between performance and cost. The Berkeley Humanoid Lite utilizes a design that prioritizes modularity. The actuators are designed to be replaceable and serviceable by a non-engineer. This means the torque density is lower than a commercial unit, but the cost is significantly reduced. The trade-off is weight and speed. A lighter actuator might not provide the same explosive power for jumping or running, but it allows the robot to perform basic manipulation tasks without draining the battery in minutes. Now consider the materials. To hit that aggressive price point, the structural components cannot be machined aluminum or carbon fiber. The open-source projects rely heavily on 3D printed polymers. This is a significant shift from the manufacturing processes used in industrial robotics. The trade-off here is between durability and accessibility. A 3D printed joint is lighter and cheaper to produce than a cast metal one, but it may wear out faster under high stress. The engineers have to design around this limitation by distributing loads across multiple printed parts, rather than relying on a single heavy component. This requires a different design philosophy. It is about additive manufacturing constraints rather than subtractive machining. You are designing for the printer, not the mold. Sensors present another layer of complexity. A humanoid robot needs to know where its limbs are in space and how much force it is applying to the ground. In high-end systems, this data comes from expensive encoders and force-torque sensors embedded in the joints. For the open-source platforms, the strategy is to use off-the-shelf components. This means relying on standard inertial measurement units and simpler encoders. The engineering trade-off involves calibration. Because the sensors are not as precise as the industrial equivalents, the software must compensate. This is where the Asimov software framework becomes relevant again. Even though the hardware is less precise, the software can learn to correct for the drift and noise. The semantic safety layer can ensure that if a sensor fails, the robot does not injure itself or the environment. It is a safety net for physical limitations. The cost of these sensors and actuators is what drives the $20,000 target. If you were to source the same components used in a Boston Dynamics robot, the price would be an order of magnitude higher. The open-source community achieves the lower cost by accepting compromises in speed and payload capacity. A commercial robot might lift 50 kilograms. An open-source version might lift 5. This is not a failure of the technology, but a strategic choice. It allows researchers to focus on the algorithms and the control systems without needing to invest in heavy industrial infrastructure. It democratizes the field by making the hardware affordable enough to buy in a small batch. This divergence between physical hardware platforms and AI safety frameworks is the defining characteristic of the current open-source robotics landscape. We have the hardware projects like the Berkeley Humanoid Lite and the AGILOped, which handle the physical constraints of actuators, materials, and sensors. Then we have the Asimov V1 software, which handles the safety and alignment constraints. They are separate silos right now. The confusion about the robot existing stems from the expectation that these two domains should be unified. But the engineering reality is that building the body and building the mind are two different problems with different timelines and different constraints. Future research must clarify whether these distinct projects will eventually converge into a single open-source ecosystem. The trajectory suggests a trend toward integration. As the hardware becomes more reliable, the software can become more ambitious. The community engagement data from forums and repositories indicates a sustained, long-term development cycle. This is not a linear corporate R&D path where a product is released and then forgotten. It is iterative and crowdsourced. Individual developers are solving specific problems, like improving the battery life of a printed joint or calibrating the sensors on a budget. This grassroots effort is what makes the $20,000 goal achievable. It relies on the collective intelligence of the community rather than the budget of a single corporation. Here's the thing about this ecosystem. It is not just about making a robot cheaper. It is about making the technology transparent. When you buy a proprietary robot, you do not know exactly how the joints are engineered or why the software makes certain decisions. With the open-source hardware and the safety frameworks, you have full visibility. You can see the trade-offs. You can understand why a printed joint might fail under certain loads. You can audit the safety constitutions to see if they align with your own values. This transparency is the real value proposition. It allows for faster innovation because the community can build on each other's work without starting from scratch. The convergence of open-source hardware with advanced AI models signals a future where high-fidelity physical intelligence becomes accessible to individual developers. However, we must remain clear about what exists today. The Asimov V1 name belongs to the safety framework. The physical robots are the Lite and the AGILOped. The $20,000 promise is tied to the hardware, but the intelligence is tied to the software. Both are essential. One without the other is just a box of parts or a program without a body. The field is moving toward a unified vision where these two strands of development weave together. Until that happens, we must appreciate the individual achievements. The hardware engineers are solving the physics problem. The software engineers are solving the alignment problem. Together, they are building the foundation for the next generation of robotics. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.